Hey guys, today we're going to be talking about colligative properties. So I'm going to give you a little background on some of the ones we have, and then in later videos, you'll be able to see how we can apply the concepts we learned today to actual problems. So first and foremost, what is a colligative property? So a colligative property is a property that depends on the concentration of the solute, but it doesn't depend on the identity. So that's a little confusing. So let's kind of go into an example here that we can see. So we have sodium chloride, and then we have glucose, C6H12O6. When we look at colligative properties, we want to figure out what does our solute break down into when we dissolve it in water. So to do that, let's figure that out. Sodium chloride is ionically bonded. So when we dissolve it into water, it's going to break up into our sodium ion and our chloride ion. Glucose, on the other hand, is covalently bonded. It's not going to break up into anything when we put it into water. It's just going to stay itself. So because of this, we can see that for sodium chloride, we now have double the amount of particles that we started with. And for glucose, we stay the same. So keep that in mind as we start explaining things. So our first colligative property is vapor pressure. So there's an equation that goes along with this. So we have the pressure of our solution is equivalent to the mole fraction of our solvent times the pressure of our solvent. So let's kind of break that down further. What is the mole fraction? The mole fraction is the moles of our solvent over the moles of our solution. So this is just telling us, if we look at the total amount of moles in our solution, what is made up of the moles of the solvent? So that's what that mole fraction is, and that's why we call it the mole fraction of the solvent. So just remember when you're solving vapor pressure problems that you have your moles of your solvent on top and then the moles of the solution on the bottom. So that's the mathematical way that we can solve vapor pressure. Now let's kind of think of it from a very simplified conceptual stance. Our vapor pressure is going to lower as more solutes are added. So the whole purpose of colligative property is to basically tell the scientist what happens when we put in solute into a solution. The first question is what happens to the vapor pressure? So the vapor pressure decreases as more solutes are added. This is because the mole fraction decreases. So let's kind of think of this by looking at these little drawings. On the left-hand side, we only have 3 solutes. They're in pink. On the right-hand side, we have a lot of solutes. They're also in pink. Now, vapor pressure is the pressure that the water molecules are going to put back on the solution when they kind of boil, right? So you can see those little arrows there. That's the water trying to escape. Once the water escapes, then it can put that vapor pressure back onto the solution. So if we look on the left, when there's not a lot of solutes, it's really, really easy for the water to escape. Because of that, it's able to have a pretty standard vapor pressure. But on the right side, it's difficult for the water to escape. They have to go in and out of the solutes. And because of that, the vapor pressure isn't going to be as big because it's very, very difficult for them to escape. So that's just like a diagram that can help us figure out why exactly does the vapor pressure decrease as more solutes are added? Well, it's because it's harder for the water to boil and then put that pressure back on the solution. Yep. Okay, so now let's think of boiling point elevation. So here's our equation right there. So we have the change in temperature is the temperature of the solution minus the boiling point temperature of the solvent equals IKBM. So again, kind of a lot of things in that equation. So when we look at the M there, that stands for molality. Molality is different than molarity. Molality is the moles of our solute over the kilograms of our solvent. So if you remember, molarity is moles per liter. But in this case, we have kilograms on the bottom. Now, the real question is, what is I? So I is the Van Hoff factor. It's the number of particles a substance becomes when it dissolves. So if we go back to the original example that I gave with NaCl, it dissolves into two different particles. So it would have a Van Hoff factor of 2. So if we look at another example here, potassium chloride. Potassium chloride is ionically bonded, so it splits up into a potassium ion and a chloride ion when we put it in water. The number of particles a substance becomes when it dissolves is the I value. So the I value of potassium chloride is 2. So again, let's switch over to the more conceptual side of boiling point elevation. So we know that liquids boil when the vapor pressure equals the outside pressure. That's how you get the boiling point. So we talked about on the other side that our solutes are going to lower our vapor pressure. So if we have more solutes, the solutions need to boil at higher temperatures to compensate. So think about it. Our outside pressure is staying the same in our solutions, right? But if we put a lot of solute into a beaker, now our vapor pressure is significantly lower than it was before. So now, to boil, the temperature needs to rise a lot more to reach that vapor pressure that equals the outside pressure. A way you can think of it is that the solutions need to boil at higher temps, right? But just think of those higher temperatures as the heat, right? We have more heat, which provides more energy, and that energy gives us the ability to boil our solution.